Welcome to Ask and Learn.
Okay, so this is a nice classic problem. You have this coax cable. You know what? I'm going to make a huge drawing. I would say that's a good low-hanging fruit sort of tip. Big drawings. If this will let me undo. Okay. Some kind of lag here. I'll just erase it, I guess. Okay, lag is over. Time to make a huge circle. Okay, so here's the inner, here is the outer. So the inner is like this, and then, yeah, and then the outer is just a shell. So I will just keep it as a line. And so the first question asks to find the electric field somewhere within here. So you're given like this radius, you're given the radius of the outer thing, and then you want to find the electric field in between. Oh yeah, I guess I'll just go ahead and write out the givens, although it really will clutter up this board. You know what? I'm going to do it on another board so I can keep it a bit less cluttered. So Q1 equals 3.4 times 10 to the minus 12 coulombs. Q2 is minus 2.00 Q1. Sorry for that ugly zero, but I'm sure you know what I mean. R1 is 1.3 times 10 to the minus 3 meters, because millimeters. R2 is 10.0 R1, and then the length of the whole thing is 11 meters. And you know what? I love to double check numbers because I don't know, it's just part of my practice to check at different points. So 11 meters, yes, 10, 1.3, 3.4 10 to the minus 12. And then, oh, I forgot the negative here. Uh-huh. And are those all the givens? Okay, yes. And then the goal is to find it first at r equals 2r. Okay, so for A, then I'll go ahead and label it Q1, Q2. And so, and I'll just label that equals 2Q1. Okay, so our goal is to find the electric field here. Sorry, this is like really not to scale. It should probably be like more like here or something. Okay, R1 equals, maybe not R1. Let's use R. R equals 2 R1. I'm gonna drop those zeros, sorry. Okay, so basically you might say, okay, well, I know that the inner charge is going to contribute to the electric field here. What about this outer charge? Maybe it'll like lessen it. And it kind of comes from the symmetry of Gauss's law that you really, to find the electric field here, you draw a Gaussian surface. So I'll use red for Gaussian surface. And you really only need to consider the charge enclosed within the Gaussian surface. And you could probably also argue it through some kind of Coulomb's law, like adding up all the charges and showing they cancel. It sounds like a mess, but I think and maybe there's a more cleaner way to state this. But if you just kind of follow Gauss's law by the letter, you only need to concern yourself with the charge enclosed within a Gaussian surface. So to find the field here, I will completely ignore Q2. So yeah, by Gauss's law, I do my surface here, and I can say E times 2 pi r. Well, I'm not going to do that because I was going to kind of argue it, but in general, but I'll just say that like solving this problem is the same, solving the problem of finding the field right here is the same problem as you would solve for a infinitely long wire. And so I'm just going to quote that result where you get that E is lambda over 2 pi r epsilon naught. And if you're not sure how to get that, I'm sure it's somewhere in the book or even just Googling it. It's a very common derivation and it's in the radial direction. So now we just need to plug in our givens. So lambda is the charge per unit length. So on Q1, so this is the inner Q1 divided by length 1 times 2 pi r, and then r is this, and then epsilon naught, and this is in the r hat direction. So then if you like plug in your Q1, oh, I guess it shouldn't be L1. I'll go ahead and kill that. And then 2 pi and r is 2r1, epsilon naught 8.85 10 to the minus 12. Then maybe you'll get what I got, which is, drum roll, 2.14 newtons per coulomb in the r hat direction. So that just means that it's pointing radially outward. So I'll draw like a little vector to represent that. Maybe I'll draw a few. So here's the electric field radially outward. I'm just going to double check the calculation. 3, 4, 10 to the minus 12, length 2 pi r, and epsilon naught. Okay, wonderful. And so that takes care of B and C. And then for C and D, it's asking about 5R1. So when I first read that, I was like, oh, I thought they were going to ask about like somewhere outside the whole system, because that's still like in between. But maybe they're really driving home the point that anything in between only depends on the inner conducting rod. Because like, yeah, anywhere where R is less than 10 R1, it should only depend on the inner conducting rod. So you would just do the same thing, except for you would want to say R is now 5R. So I'll go ahead and kind of label what I just said. So there's A. So B is out. C, same math, except, oh man, this thing writes so sloppy. I actually don't have bad handwriting, which you might find surprising. I'm not sure what it is about this pad. Okay. Except R is equal to 5R1. So when I plugged that in, it reduced the answer a bit to 0.855, and then still outward until that's D, because it's in the R hat, positive R hat direction. Okay. And then for E and F, so it's asking about how much charge is accumulating on the inner and outer surface. I'm just going to double check the wording. Inner and exterior surface of the shell. So this is a really common problem. So it's that I've seen, at least in the physics classes that I've TA'd. So it's probably a good idea to like master this because it's just so clever. So the idea is that you have Q1 here. How much charge is going to be here? Like, and will it be affected by this total charge? And so I've done this argument in other videos, but I will go ahead and do it here. So the idea is to get the charge in the inner surface. First, going to draw the inner surface. Oh, didn't close. And now I'm going to draw a Gaussian surface. So I'll use red for Gaussian surfaces in this video. Who knows what I'll use for the other videos. Maybe I'll still use red. Okay. So here's my Gaussian surface. And so I know that in this surface, it is a conductor. And if it is a conductor, the electric field 0. And therefore, and the only way for the electric field to be 0 by Gauss's law is for the total charge enclosed to be 0. So therefore, if you have Q1 here, you definitely have to have minus Q1 total on this sort of edge. So, oh, those look like dots. Okay, so this is supposed to represent charges. And so, great. And now to get the charge on the outer, then you don't have that constraint anymore, but you do have the constraint that charge is conserved unless you physically transfer it. So we know that the total charge on this outer shell has to be minus 2Q1. If you already got minus Q1 on the inner, it's just accounting. That tells you that you have minus Q1 on the outer. And so because it sums up to minus 2Q1. So the answer is coincidentally the same. Minus Q1 minus Q1.